In this video, you are going to understand the concept of linear regression. What is linear regression? Linear regression is a type of supervised machine learning that is used to predict a value based on two or more relationships. Okay, being said that, it is different from classification in the sense that classification is used to categorize input data based on the category or label. For this particular video, we are going to be using the mobile price data set. So I have the modules already imported from NumPy down to the metrics of the linear regression. So let's load in the data set. So say df equals to pd.read underscore csv. Then we say the mobile phone price data set. So let's display the five rows and let's see what we have. df.head. Okay, so this is what we have in the data set. You can see the brand, the model, the storage, the RAM, the size, the camera, the battery capacity, and the price, which is the target variable. Now, this is not based on accuracy, but based on assumption. It's not based on accuracy, but based on what? Assumption. Okay, so the next thing we're going to do is to check for missing value. So we'll say df.isNote.sum. Okay, so there's no missing value. Since there's no missing value, the next thing for us to do is to convert all the categorical columns into numerical columns. Because if you do df.info, if I go there, so you can see practically all of them are object. Now, there's something about the price. Look at the price. The price is not supposed to be object. The price is showing object, which is very wrong. So first, let's convert the price to what? To integer. So I say df column of price equals to pd.to underscore numeric df the column of price. So let's do the info again and let's see what we have. df.info there's an issue with that particular column. So let's see what the issue is going to be. Okay, so you can see that in this particular column, you still have the dollar sign. There's still one value that has the what? Dollar sign. So let's try to remove the dollar sign first. So say df, the column of price equals to df, the column of price dot str dot replace. Anywhere you see the dollar sign, replace it with an empty string. Then after that, it will now convert it to numerical. You see that it's going to work now. Another error again, you can see there's comma. There's one that has comma, so we have to remove that one too, just as the way we remove the dollar sign. So I'm going to copy this line of code, paste it here. Then I'm going to put the comma there to replace it, then we'll run it. Okay, so you can see that everything is okay now. So these other columns that are object, we are going to convert them to what? Numerical columns using the label encoder. How does the label encoder works? It's going to arrange the value in each column in ascending order. Then from the minimum to the lowest, is going to label it from 0 down to the last what? Value. So we say numerical column, or categorical column rather, categorical column equals to df dot select underscore dtypes include any column that is object and any column that is category. So say encoder equals to label encoder. They will come over here. We say for x in cat underscore column df x equals to encoder dot fit underscore transform df x. So let's see what we have now. So df dot what? Head. So we are good to go. So the next thing we are going to do is to separate the independent variable from the dependent variable. Y is the dependent variable, which is going to be price, and x, the independent variable, is going to represent from brand to battery what? Capacity. So we say let independent variable be x, and we say df dot drop price the dollar sign. Let me copy the actual sign so that there won't be conflict. Dollar sign, then axis equals 1. Y, which is the dependent variable, is df, the column of price. Then let's split into train and test data set. We can use the x and y to train directly, but we have to evaluate to check the error margin between the original and the predicted outcome to be certain that this particular algorithm that we are using performs better and learn better from this data set, and it is ready to be deployed. Okay, so we say x train, x test, y train, y test equals to train test split from x and y. Then the test size should be 0.2, which is 20%. So we are going to start with the base linear regression algorithm, which is linear regression itself. So we say model 1 equals to linear regression. So for linear regression, these are the what? Parameters. So we say model 1 dot fit x train and y train. So the data, the algorithm has learned from the data and it is ready. So let's evaluate it. It is ready, but let's evaluate it. So say print mean absolute error of y test. But first we have to predict. So we say predict 1 equals to model 1 dot predict x test predict 1 mean absolute percentage error, mean squared error, mean squared error, then root mean squared error, root mean squared what error. So let's evaluate it. Okay, so you can see for this one, the mean percentage error is 50%. So let's check the R2 score, which is the goodness, which is the one that checks the what? The goodness. So the R2 score is what? Positive 61 what? %. So let's try another model. Let's try another what model? Let's try decision tree regression, which is an advanced algorithm. Model 2 is decision tree model 2. So let's evaluate the decision tree also. Okay, so you can see that this one is better. So that's the essence of using more than one or two algorithms. One will always be what? Better. So based on this particular data set, the decision tree is better. So like I said, linear regression is based on what? Assumption. So we can predict now that if we go into the market, the price of a phone will be this or the price of a phone will be what? Will be that. So let's check the difference between the original outcome and the predicted outcome. So say outcome, we have a dictionary. Outcome, we have a dictionary. Then we say actual value is y test, y the predicted is print what? Print 1. df2 equals to pd dot data frame out. So let's see df2. So you can see. So for this particular line, what actual value is 469, but the predicted value is what? For what? 99. You can see that some there are difference and some there are no what? Difference. Okay, so we see in our next video.